Hello friends, welcome to this new video. SAP2000 application of the direct displacement based design of frame-shear wall system. The numerical background, mathematical background of this design we have seen in the previous video. Now let us apply those calculations as well as the actual implementation in SAP2000 software. So our question is like this: to design a 10-story building, which is frame-shear wall building, target depth is 2.5%, hazard level is 0.4 G, corresponding to EC8 spectrum at 0.4 G level of seismicity. The frame shall carry 30% of the base shear. Consider 20 mm bar for shear wall and say columns etc. also. 3.3 meter is the story height except for the ground floor, which is 4 meter high. Yield strength of rebar is 500 megapascals, concrete strength is 30 megapascal. Wall length is 5 meter, beam size is 0.5 by 0.6 meter, depth is 0.6 meter. Column size is 0.6 meter by 0.6 meter. Wall thickness, that is the shear wall thickness is 200 millimeter. Slab thickness 120 millimeter. Outer wall is 1 brick thick and inner walls are half brick thick. Post yield stiffness ratio is 0.1. Plan is shown below. Live load intensity is 3 kN per square meter. Now we shall make some approximation in some places, because our idea is not to get the exact building, but our idea is to expose you to the application of the software to the direct displacement based design of dual system buildings. The plan is rectangular with 5 bays along the long directions and 3 bays along the short direction. All the bay lengths are 5 meter. The red lines, small rectangles, are the shear walls, whose length is 5 meter and thickness is 0.2 meter. Columns are all square columns 0.6 meter by 0.6 meter. We are taking columns uniform through the whole height of the building for simplicity. So number of columns here is 24 numbers and number of walls is 4 numbers. Remember, I have not calculated how many walls are required or what should be the thickness. That calculation will come later on in some other video. Here we are trying to show how these things are implemented in this SAP2000 software. Slab area we can find out. This 25 meter by 15 meter is 375 square meter. Length of all beams, if you add up, you get 190 meter. Length of one brick infill, which are the peripheral lines, is 80 meter. Length of half brick infill walls, which are the interior walls along the beams, is 110 meter. Now we have to compute the mass in the different floors and then the roof, so that we can carry out the further calculations for the DDBD for dual system. So weight of slab is thickness into 25 equal to 3 kN per square meter. Slab finishing, including say tiles etc., we have taken as 1 kN per square meter. Total slab unit weight is 3 plus 1, 4 kN per square meter. Total slab weight per floor you can calculate now. This 4 into area of the floor is 1500 kilonewton. Weight of shear wall you can calculate, because there are 4 shear walls, 0.2 meter thickness, 5 meter length, 3.3 meter height, and unit weight of concrete is 25 kilonewton per square meter, cubic meter, 330 kilonewton. Weight of infill wall, the outer walls are 200 millimeter thickness and inner walls are 100 millimeter thickness. We are considering modular bricks and 3.3 meter is height, and unit weight of brick masonry we are taking 20 kilonewton per meter cube. So this is this Weight of columns, similarly we can calculate 24 columns of size 0.6 by 0.6 meter, 3.3 meter high, and unit weight, so this was 713 kilonewton. Weight of beams per floor, we have considered already slab thickness 0.12 meter. So from the overall depth, this I am subtracting so that we get the rectangular part of the beam. So 190 is the length of beams, then this depth and the width, unit weight, it gives 1140 kilonewton. Live load we have taken 3 kilonewton per square meter. So total live load per floor is 1125 kilonewton. So now we can calculate total weight per floor for seismic calculation. So adding all this slab, then shear wall, then infill, then column weight, then beam weight, and finally live load. Live load we are taking 25%. Say in IS code, if the intensity of live load is 3 kilonewton per square meter or less, then 25% of this live load is to be considered as seismic weight. So we have taken a multiplier 0.25 here over the total live load, and finally we get this kilonewton per floor. So mass, we convert this to Newton, then divide by 9.81, so this much kg. For the sake of simplicity, we are just rounding it off to 5800 kg. Roof mass will be less. In the roof, live load should not be considered, so live load is not taken, and slab weight is same as the earlier. Other weights are taken as half, because it is assumed that half of the height of the story is carried to the roof level. So that way it is calculated. So it is coming as 413100 kg. So you have calculated the floor level masses and the roof level mass. Now we can calculate the height of inflection we have discussed in previous video. We make a tabulation with MIHI, and summation of this MIHI. Summation is found out here, and this column is MIHI divided by this summation. So this comes in fractional values. Then total shear in the different floors, relative shears. These are not true shears, relative shears, because these are the relative forces we have placed. And the moment, how to calculate, we have discussed in previous video. The shear carried by frame is 30%, so 0.3, and so wall equal to total minus frame, this much. And wall moment, how to calculate, we have discussed in a previous video. So finally, out of this table, you get the water-turning moment of the frame as 23.741 kilonewton meter, and water-turning moment of the wall as 12.945 kilonewton meter. So from this very table, we calculate the inflection height. So simply put this wall moment in the horizontal axis and height of the building in the vertical axis, and plot these values, and we get where the bending moment diagram is 0. Here is the inflection height, which comes out to be 23.8 meter. Now we find the equivalent single degree of freedom system properties. For that tabulation we have discussed in earlier videos. So height, mass, delta IY for the wall, the yield displacement of the wall, then delta I for the ith wall, then products mass into delta I, then product mass into delta I into delta I, and finally product MIHI delta I. Then you find out the summation of this column, and this column, and from the formula available, this divided by this is the delta D. So delta D is 0.502 meter. ME equal to this divided by delta D, so it is 4267831 kg, and HE effective height equal to this summation divided by this first summation. Then you have to calculate the ductility of the frame, mu f. So ductility of the frame changes with flow. There is this formula we have discussed earlier in previous video. Delta is the displacement of the ith floor level. Delta I minus 1 is the displacement at the bottom floor level. Theta yf is the yield rotation of the frame, which is given by this formula, and we have calculated the value as 0.0142. So at every floor you will get a mu value for the frame. So it is hi delta I and the mu value we have written here. Then sum it up and divided by the number of story, which is 10 story high building 10. So mu f is 2.146. Well, then we find the damping in the equivalent single degree of freedom system. You start with the calculation of the LP, the plastic hinge length in the wall. So there are two formulae available, out of the whichever is smaller is to be taken. So it is coming out as 1.516 meter. Then yield curvature of the wall is given by twice epsilon y by LW. So this comes out as 0.001. It will be per meter. Then the wall ductility is mu W given by this formula, which comes out as 9.703. And mu f in the previous slide we have got 2.146. So mu SDOF is mw mu w plus MOTF mu f divided by summation of mw and MOTF. So this comes out as 4.812 in percentage damping in the equivalent single degree of freedom system. The trial time period given by empirical formula is n by 6 into ESD. N is the number of stories 10, so it comes out as 3.656 seconds. Now find the damping in the wall by this formula, where R is the post-tilt stiffness ratio, which is 0.1. The rest of the things are known to us, so it comes out as 13.57%. Similarly, for damping in the frame, it comes given by this formula and it comes out at 8.71%. The damping of the equivalent single degree of freedom system is weighted average. So it is xi f MOTF plus xi w MW upon MOTF plus MW. So this is coming out as 10.43%. So this is the damping in the equivalent single degree of freedom system. Now you draw the displacement spectrum corresponding to EC8 soil type B and at seismicity level 0.4 G. How to plot this displacement spectrum we have discussed in previous video. So this is the displacement spectrum at 10.43% damping. Our delta D is 0.502 we have found earlier. So at this, if you draw a line, horizontal line, which it cuts the damping line here, and if you draw a particle line downward, here you get the effective time period. So it is coming out as 4.2 seconds. Now trial time period was different from this, so it will require another trial of calculation. So these calculations are, in place of trial, T trial, you put this T value 4.2 seconds in the previous formulae of xi wall, then xi frame and xi equivalent single degree freedom system. So with all these similar calculations with the previous formulae, it is now coming out as 10.42% damping in the equivalent single degree of freedom system. Earlier, if you remember, it was 10.43. It is shown here also. So the difference is marginal. So we shall take this, we shall not make any further iteration. We only take time period as 4.2 seconds. We get K equal to 4 pi square ME by T square. So 9551412 kilonewton per meter. The base shear is K into delta D. So this comes out to be 4796856 kilonewton. So this is the design base shear for our case. Now this base shear we have to distribute over the floors. So distribution is very simple. Put the masses, then delta I values, then Mi delta I, and this VB is to be distributed in proportion to this Mi delta I divided by summation of Mi delta I. So these are the different forces you get, and finally you can make a cross check by adding up all these. You should get the base shear which is coming. Just immediately previous video, PVD 16, we had made a mistake in this tabulation. We had put HI here and MIHI, so it was wrong. It should be delta I and MI star delta I. So here is this SAP2000 model in version 21. It is 10-story building. We have put shear wall on the 4 sides that I will show in the extruded view. Before that, let us see some basic things that we have done with this model. And one thing I need to mention that it is not teaching the SAP2000. I assume you already know SAP2000 software use. Otherwise, you can write in the comment box. We can have some classes, some videos on SAP2000 usage. So we have taken the materials. So materials we have taken is M30 concrete and HYSD 500 rebar for all the reinforcement bars. The other values we do not require. You may delete also if you require. I think one you cannot delete. It is maybe default. Yes. Now let us go to this section, define section properties, frame sections. We have taken beam section, which is 0.6 meter deep and 0.5 meter wide. In the concrete reinforcement, you have to mention that it is beam with M3 hinges. Then we have taken a column section, naming it COL, and the section is 0.6 by 0.6 meter. We have not changed the beam size and column size over the height, because here it is not the aim to design the building thoroughly and correctly. It is to show how delivery method to be applied in the SAP2000 shear wall building design. In the concrete reinforcement, you have to show it as a column, M2 M3 hinges, and reinforcing bars are these. And we have put the main bars as 20 millimeter diameter. Then we have taken shear wall. Now shear wall in the long direction of the building and short direction of the building are to be with different orientation. So short direction shear wall is like this. Depth is 0.2 meter and width is 5 meter. So this is coming like this. In the reinforcement, you see here we have taken column. Now we are making one assumption here. The shear walls are modeled as wide columns. This will lead to some inaccuracy, but we shall try to compensate this inaccuracy by considering the actual hinge values of the shear walls instead of the columns. So in the column hinges, we shall substitute the shear wall hinges later on. But however, the basic model is a wide column system for the shear wall. The other model is the what is called shell element model. And also in some cases like Perform 3D, you can use the wall element directly. In SAP2000 it is not there, but you can use what is called the shell element for the shear wall. But in the shell element, the computation of the plastic rotation is a bit clumsy. Whereas the current plastic rotation, you have to use some software to calculate that. So in the wall also we are taking 20 millimeter diameter bars. In the list of the bars you can select. So we have selected this 20 mm diameter bar. And the confining reinforcement 10 millimeter diameter, etc. And you have to put reinforcement to be designed, not checked. So then long wall is just the reverse. If you see it, the depth is 5 meter and width is 0.2 meter, because the orientations of the walls are different. It is also again a M2 M3 hinge column type. There is shear wall modeled as wide column. So in the different beams, and over the beams we have put the wall loads, we have put the slab load, etc. If you click any one and go to assign frame load distributed, and if you stick here say slab live load or say slab dead load is there, it will show the all slab loads. So we have the two windows. In the left hand window, the 3D view of the building is shown, and the right hand window, the long directional frame is shown. This cyan color is showing the shear wall. You can see the expanded extruded view. If you go to the general options and give extrude, apply, yes. So it is showing, you see, this is the shear wall and the others are columns. This is the shear wall has been modeled as white columns only. So we have 4 shear walls on the 4 edges of the boundary lines of the building. We have applied all the loads, etc. You can perhaps see the loading by showing loads, and the label is there. Concrete is showing the member assignments. Because the model is already logged, we cannot do much operations on this, so all the loads have been applied, and you can see the loads in the assign. No, it will not show in the logged condition, it will not show. So time histories have been run, and you can get the through display plot functions. You can select the joints. The joints perhaps we have discussed here. If you go to the plan, these are the joints put artificially by drawing special joints at the center of the each slab. So each joint has its level, say 135. Similarly, at the roof level, the joint is level is 130. So if you want to see the displacement function at the joint at the roof level, then you take this, add to this command and show the display. Then it will show you the displacement history of that floor at the central node. How to capture the data behind? You can go to the file and give printables, and you can print to a Excel file. So that way we have printed it to Excel file, and we can show the files here. This is the Excel file. So floor by floor we have taken the displacement history. This is roof level, these are the displacement history values, and these are the timings. Similarly for floor 9, and to find the interstory drift, we simply take the absolute value between the difference of the top floor and the bottom floor, absolute value, that gives you the interstory sway, divided by the height of the story 3.3 meter, then you get the interstory drift. And if you multiply it by 100, you get the interstory drift in percentage. So these values are in percentage. Now for this very drift between the roof and the 9th floor, you have to take the highest value out of all the drifts. So it has come out at 0.459, etc. Similarly, for the drift between the floor 9 and floor 8, take the absolute difference between the displacement of the floor 9 and floor 8, multiplied by 100 and divided by 3.3 height of the story, you get the interstory drift ratio, which are shown here in this column, and take the highest value, which is coming 4.2%. Similarly, the interstory drift ratio between all the floors have been obtained, and finally we want to plot these interstory drift ratios in graph. So these are the story and the height of the stories and inter-story drift ratio in percentage as we have obtained from these previous calculations are shown here. So this is called ideal diagram, inter-story drift diagram. This can be shown in two ways. One is shown in the first diagram, where the ideas are in the horizontal line and the heights are there in the particle axis, and all the points are consecutively added up by straight lines. So this is one way of showing. Another way of showing the inter-story drift diagram is by drawing lines like this. So what does it indicate? It indicates that for the first story, whatever below the drift, that remains constant after that height, then it changes a little, then goes to the next story and changes a little like that. For example, at the roof level, your drift is this much, which is about 4%. For the next story, 9th floor, the drift is here. So it is about 3.3%. So this way, it is another way of showing the inter-story drift diagram. Here we have drawn the line for design drift. So our design drift was 2.5%, which is shown by dotted line here. And we see that our achieved drift, these are the achieved drift, has overshot over the 2.5%. It is much higher, it is 4%, slightly more than 4%. So our design is not very perfect. This is because in the direct displacement based design, there is nothing said regarding the sizes of the members. So arbitrarily we have taken the members, and so the results are also arbitrary. Furthermore, the shear walls were not designed appropriately, or in the direct displacement based design, the shear wall thickness, length, etc. you cannot obtain through theoretical approach. So with all the limitations of the direct displacement based design, we see that the drift could not be achieved. Drift has been found to be more than the design drift. So this is one limitation of the direct displacement based design. Now let us see the hinge results on the hinge results can be shown over the 3D, or it can be shown. Let us go to standard mode. So this is the standard view now. This is in plan. Let us put it in. We have applied the earthquake load along the short directions. Let us see here, define load cases. The nonlinear time history analysis is here. Modify show. You can see what is there internally here. It starts from an initial stage, continue from the previous stage, which is the loading, direct vertical loading. Then the direction is U2, means along the y direction or along the short direction of the building here. We have analyzed for only one direction, and this is the spectrum compatible ground motion that has been generated compatible to the EC8 at 0.4 G level for soil type B. So this is the, and here is the scale factor. The scale factor is equal to 0.4 G, as it was done at 0.4 G level for the EC8 spectrum. So this is 3.924. So with this scale, etc., the time history analysis was carried out. Perhaps you can see other load assigns. No, it will not show you in the locked condition. It will not show you, but in define you can see. One thing is mass source you have to show. So with the mass source you have to give all the, say, self load, infill load, then slab live load, slab dead load. Slab live load you have to give a percentage as per some codes. In Indian code it is 25% of the live load for live load intensity up to 3 kN per square meter. Then you can see the section properties we had taken earlier, the frame sections, beam section, column section, wall along the long, wall means shear wall along the long direction and wall along the short direction. For example, if we want to see the properties here, thickness is 0.2 and width is 5 meter. So it is modeled as a white column, and material is M30 concrete. Then defined, we can see load patterns are, we have seen infill and lateral live load, and these are the FX and FY. The earthquake load that we have calculated in the previous part. some slides in the back side that all the base shear distributed over the floors. These forces are put at the nodal points of the floors, and these are put at the both directions Fx and Fy. You can see the load combination, what load combinations will be used. These are not total load combinations but simpler. Dead load, live load, dead load, live load and Fx, dead load, live load minus Fx, dead load, live load plus Fy, and dead load, live load minus Fy, this much only. And in the material also you have to see that you have to use the expected strengths. So if you go to the materials, say M30 concrete, then you see here we have not put, if you go to Newton millimeter, see it is 45 not 30 because we have put the expected strength in design as well as in analysis. So expected strength of concrete is 1.5 into FCK, 1.5 into 30 which is 45. Okay, similarly if you go to the rebar, then you can see the strength is not 500 but 625, that is 1.25 into 500, which is the expected strength to be used in this damage based design. So what else we can see? Define load pattern, load cases. There are two cases here. Initial one case where you have put all the loads, the dead loads. Under dead load, this load pattern, so all these loads and appropriate load factors. Here you have to give the directions. You see we have given direction along the y direction or short direction of the building. So U2 you have to give, and joint we have given at the roof level central nodal point. So this is the initial load which is applied, and then the nonlinear time history case we have seen already. This is starting with that initial case, and it is along that y direction, and it is with SCGM, the spectrum compatible ground motion. Let us see what is the spectrum compatible ground motion. Define, if you go to function and time history, this spectrum compatible ground motion we have taken as per the Eurocode 8 EC8 at 0.4G level. So you can see the time history function. Yes, this is the time history function. We have taken the background earthquake as the El Centro earthquake, NS direction, and with that background earthquake, for that design spectrum of the EC8, a spectrum compatible ground motion has been generated through Seismic software, and this is what you are seeing here. So I think we have discussed the background different. Now let us go to the hinge patterns. So if you simply go to the deformed load and under nonlinear time history analysis at say last step is I think 31 second. At this second, what is the damage state? It will show you. Okay. So damage state, these pink colors are showing the IO level hinges. So IO level hinges have been formed. In the shear wall there is no hinge. You can see here. If we apply the same thing, 31 in the frame, we can see it here. These are the pink color hinges or immediate occupancy level of damage in the systems, and it is showing some intermediate frame view. If you want to see the shear wall condition, then you go forward. Yes, this blue color is shear wall, and no hinge has been formed here because load is perhaps not very high. So hinges are there in the beams only. Hinges are not there in the columns because by capacity design, columns should remain elastic, and that can be achieved by regulating the column to beam capacity ratio, C by B ratio, more than say 1.4 or like that. In Eurocode it is 1.3, in Indian code it is 1.4. So if you maintain that, column should not fail. I think in the nutshell we have discussed the background modeling, the Frame-Shear Wall in the SAP2000 software, and in the Excel sheet we have made the calculation for interstory drift, which are found from the differences of the displacements at corresponding time between the upper floor and lower floor. Thank you for coming with me up to here. So in this video we have not gone to the details of application of SAP2000 software. All the steps are not clarified nicely. If you want to have knowledge on SAP2000 software, you can write it on the comment box, and I can take gradually from the elementary level the creation of model, etc. with SAP2000 software. Please share the video, like the video, subscribe the channel, and put your comments, your suggestions in the comment box. Thank you again.